Today's show comes to you courtesy of the genetic code for Spectrin. This isn't just a sequence of letters. It's the ancient, mystical blueprint that dictates the very architecture of your red blood cells. When this sacred text contains a single inherited typo, the entire cellular house might just collapse, leading to an endless parade of misshapen spherocytes or elliptocytes. It's a fascinating peek into the fundamental building blocks of life, revealing how a minuscule hereditary hiccup can orchestrate a grand, lifelong performance of premature cellular destruction.
Okay, let's unpack this. Imagine a tiny, vital component of your blood, the red blood cell. It's designed for a long, efficient life. But suddenly it's facing an early demise, and not from some external attack. It's from an inherited flaw deep within its own structure. Today we're taking a deep dive into the fascinating, sometimes kind of baffling world of normocytic anemias. We're specifically zeroing in on a really intriguing subset, hereditary hemolytic anemias. And for you, the medical laboratory scientists listening, our mission today is pretty clear. We want to distill the critical insights, the real nuggets about the pathophysiology, and crucially, the laboratory testing for these conditions. Think of it as, well, a shortcut to being truly well-informed. We're drawing from comprehensive hematology sources, aiming to give you that aha moment right there at the lab bench.
Exactly. And this really isn't just about, memorizing lists of facts. What's truly vital here, I think, is connecting the why behind the what's. What you actually observe under the microscope, what you see on your lab reports every single day. For medical laboratory scientists, this nuanced understanding, this ability to sort of predict and interpret those subtle signs, it translates directly into more accurate diagnoses and ultimately, of course, better patient care. It really empowers your judgment.
That's perfectly put. So maybe let's start from the ground up. Let's establish the foundations of hemolysis. What exactly happens when these red blood cells die too soon?
Okay, so at its core, hemolytic anemia is, well, just like it sounds, anemia caused by increased red blood cell destruction, hemolysis. And this destruction generally happens in one of two main places. It can be intravascularly, that means right within the blood vessels themselves, or it can be extravascularly, which is primarily in organs like the spleen and the liver, where macrophages do the work.
Okay, so destruction inside or outside the vessels. How does that show up in the lab results? What are the big flags?
Right. Well, what's fascinating is how consistently this accelerated destruction manifests in the lab. The hallmarks you'll almost always see include, first, a significantly shortened red blood cell lifespan. Obvious maybe, but fundamental. Second, this rapid turnover forces a bone marrow to ramp up production. So you'll see increased erythropoiesis, evidenced typically by an elevated reticulocyte count. And finally, you get an accumulation of the breakdown products from hemoglobin. Most notably, you'll see elevated indirect bilirubin and also lactate dehydrogenase, LDH.
Got it. Short lifespan, more production, more breakdown stuff. So within that general picture, how do we start categorizing these?
We generally classify them based on where the primary problem originates. You have the extrinsic or acquired hemolytic anemias. These are caused by factors outside the red blood cell itself, things like immune reactions, mechanical damage, certain infections.
Right, but today we're focusing elsewhere.
Exactly. Today, our deep dive is exclusively focused on the intrinsic or inherited hemolytic anemias. These result from defects within the red blood cell. And they fall pretty neatly into three main categories. You've got membrane defects, enzyme deficiencies, and then the hemoglobinopathies.
And today we're tackling those first two, the membrane and the enzymes. Okay, so with that foundation, understanding how RBCs break down too fast, let's zero in on where these inherited flaws often begin. And often that's with the very membrane of the red blood cell itself.
Right. The membrane is critical. What's unique about these membrane defects is that mutations in the proteins that make up the RBC membrane, they disrupt its structural integrity, its flexibility. This leads to abnormally shaped red cells. And these misshapen cells are inherently more susceptible to getting trapped, particularly in the spleen, and destroyed prematurely. Clinically, you'll often see features like splenomegaly, an enlarged spleen simply from that increased workload, and of course, jaundice from the elevated bilirubin.
Okay, here's where it gets really interesting for everyone working day to day in the lab. Let's delve into some specific membrane defects. Focus on their unique characteristics and, crucially, those specific lab findings you'll be looking for. First up, let's talk hereditary spherocytosis, HS. So this is primarily caused by mutations in genes coding for proteins like spectrin, ankyrin, band 3, protein 4.2. These are all essential for maintaining that normal biconcave shape and, importantly, flexibility.
Right, absolutely crucial proteins. So when you have deficiencies in these, there's a progressive loss of membrane surface area relative to the cell volume. This forces the red blood cells into a spherical shape. Those are the distinctive spherocytes we see. And because these spherocytes have dramatically decreased deformability, they just can't squeeze through the tight spots in the spleen. They get trapped and destroyed. Clinically, this translates into, well, variable anemia, jaundice, splenomegaly, and sometimes even bilirubin gallstones, cholelithiasis.
So if they're constantly getting trapped and destroyed in the spleen, what does that mean for the lab results? What are the immediate red flags an MLS should look for on their peripheral smear and the CBC?
The lab findings are truly the cornerstone for diagnosing HS. On the CBC, you might see a normal or even a slightly decreased mean corpuscular volume MCV. But here's the real aha moment, the diagnostic beacon, an increased mean corpuscular hemoglobin concentration, MCHC, often above 36 grams per deciliter. This is almost unique among the hereditary hemolytic anemias. It's a direct consequence of those tightly packed spherical cells. Less membrane, same hemoglobin.
Right, that increased MCHC is key.
Definitely. Your red cell distribution width, RDW, will also likely be increased, showing variation in size. Then on the peripheral blood smear, you'll see those classic spherocytes. They're the defining features, small, dense, lacking that central pale area. You'll also spot polychromasia, indicating that elevated reticulocyte count we mentioned earlier.
Okay. And what about ruling out other things?
Right. Importantly, the direct antiglobulin test, DAT, will be negative. That helps rule out an autoimmune cause unless, of course, there's a coexisting autoimmune process happening, which can complicate things. And the classic confirmatory test, the osmotic fragility test, it'll show significantly increased osmotic fragility, meaning these fragile spherocytes lyse much more readily in hypotonic solutions compared to normal RBCs. That's a key diagnostic test for HS.
And you mentioned treatment sometimes involves removing the spleen, splenectomy. For severe HS, that's often the mainstay. Does that come with any specific risks or post-surgical considerations an MLS should be aware of? Perhaps things reflected in later lab work over time?
That's a really important point. While splenectomy dramatically improves the anemia, by removing the main site of destruction, it absolutely carries long-term risks. Patients are at increased risk of certain infections, particularly from encapsulated bacteria. And there's also an increased risk of thrombosis, blood clots. These risks might sometimes manifest subtly in post-surgical lab results over time, maybe changes in platelet counts or specific RBC morphologies like Howell-Jolly bodies appearing.
Good to keep in mind. Okay, so from spherocytes, let's shift our focus. Another distinct membrane defect, one that literally reshapes the red blood cell into an ellipse, hereditary elliptocytosis, or HE. This one, the source says, is primarily caused by mutations in spectrin again, but also protein 4.1 or glycophorin C, different components.
Right, slightly different structural issues. These defects primarily disrupt the horizontal interactions within the red blood cell cytoskeleton, the internal scaffolding. The structural weakness is what leads to the characteristic elliptical shape, the elliptocytes. What's really notable about HE, though, is that most patients are actually asymptomatic. It's often just an incidental finding on a blood smear. However, there are severe forms that can certainly cause significant hemolysis.
Okay, so if you're suspecting HE, maybe from seeing those shapes on the smear, what are the most definitive lab findings that will help you clinch the diagnosis?
Well, the peripheral blood smear is definitely the giveaway. You're looking for the presence of elliptocytes, and typically they need to constitute more than 25% of the red blood cells. In more severe variants, you might also see general poikilocytosis, which just means a variety of abnormally shaped cells. Critically, though, the osmotic fragility test is usually normal in HE. That's a key differentiator from hereditary spherocytosis.
Makes sense. Different defect, different fragility.
Exactly. And as we mentioned, for most patients, thankfully, no specific treatment is needed.
All right. Our third membrane defect really takes the shape abnormality concept to an extreme. Hereditary pyropoikilocytosis, or HPP. Just the name sounds intense, and from the sources, it really is often described as a very severe form of hereditary elliptocytosis.
Oh, it's quite dramatic when you see it on the smear.
Yeah.
HPP usually arises from what's called compound heterozygosity for spectrin mutations, basically inheriting two different spectrin gene defects. This results in a marked spectrin deficiency, and that leads to two key features: extreme poikilocytosis, just bizarrely shaped cells all over the place, and a striking heat sensitivity. These red blood cells literally fragment at temperatures that are normally well tolerated, sometimes even just body temperature or slightly above, like 45-46 degrees Celsius in vitro.
Wow.
Yeah, clinically, patients present with severe, often microcytic hemolytic anemia with pronounced poikilocytosis and splenomegaly.
And what's the visual story on the lab bench for HPP? This sounds like something that practically screams its presence on the peripheral smear.
Absolutely. It's one of the most striking morphologies you'll see. On the CBC, expect a very low MCV, microcytosis, and a significantly increased RDW because of all the different shapes and fragments. But the peripheral blood smear is truly the diagnostic centerpiece. It shows that extreme poikilocytosis. That's the distinguishing feature. You'll see microspherocytes, elliptocytes, bizarre shapes, and numerous fragmented cells, schistocytes. The reticulocyte count, as you'd expect with severe hemolysis, will be markedly elevated.
And treatment?
Similar to severe HS, for severe cases of HTP, splenectomy is often the mainstay of treatment to reduce the hemolysis.
Okay, finally, for a discussion on membrane defects, let's unpack hereditary stomatitis. This is an intriguing one, caused by mutations affecting membrane cation permeability, particularly involving proteins like piezo-1, and stomatin. Sounds complex?
It is a bit complex, involving the movement of ions like sodium and potassium across the membrane. This altered cation permeability directly leads to significant changes in red blood cell volume and shape. We primarily recognize two main types, kind of opposites in a way. First, there's overhydrated hereditary stomatitis, OHS. Here, there's an increased influx of sodium and water into the red blood cells. This causes them to swell up and form stomatites, those cells with the characteristic mouth-like or slit-like area of central pallor.
Okay, overhydrated. Makes sense. Mouth-shaped cells.
Right. Then, conversely, you have dehydrated hereditary stomatitis, DHS. In DHS, there's an increased efflux, or loss of potassium and water from the red blood cells. This leads to cellular dehydration and the formation of various spiculated cells like acanthocytes, Burr cells, or sometimes target cells.
So these distinct mechanisms, cells getting too wet or too dry, how do those translate into the key lab findings you'll need to watch out for at the bench?
Okay, so on the CBC, think about the volume. You'll likely see an increased MCV in OHS because the cells are swollen. Conversely, you'll probably see a decreased MCV in DHS as a result of that cellular dehydration.
Logical.
Yes, but again, the peripheral blood smear is incredibly informative. You'll identify those characteristic stomatocytes in OHS or the spiculated cells and target cells in DHS. Now, the osmotic fragility test gets interesting here. It's variable. It's actually increased in OHS. Those swollen cells are fragile, but conversely, it's decreased in DHS. The dehydrated cells are more resistant to osmotic lysis.
Opposite of what you might first think for DHS.
Right, it's counterintuitive. And a crucial clinical note, especially for OHS, while splenectomy might be considered for severe cases to reduce hemolysis, it carries a unique, significantly elevated risk of thromboembolic complications, blood clots, much higher than in HS or HPP.
That's a major consideration.
Yeah, absolutely. And also, patients with DHS can sometimes develop iron overload, so that needs monitoring too.
Okay, so we've explored how structural flaws in the red blood cell, its very skin, can lead to its premature demise. But what about the machinery inside the red blood cell? The energy systems, the defense mechanisms. Let's transition now to our second major category of these intrinsic defects, when crucial enzymes fall short.
Right. The general pathophysiology here is quite profound, actually. Deficiencies in enzymes that are essential for red blood cell metabolism, they disrupt one of two key things. Either they mess up the vital energy production pathways, like glycolysis, or they compromise the crucial antioxidant defenses, like the pentose phosphate pathway. Either way, this leads directly to premature red blood cell destruction, especially when the cells are under conditions of oxidative stress or increased metabolic demand. And in the lab, you'll generally see the classic signs of hemolytic anemia we've discussed: elevated retics, elevated indirect bilirubin, and typically decreased haptoglobin.
Got it. So the first big enzyme deficiency we need to dive into is glucose 6-phosphate dehydrogenase deficiency, G6PD deficiency. This involves the G6PD enzyme, which is critical in the pentose phosphate pathway you mentioned.
Yes, G6PD is absolutely essential. It's the rate-limiting enzyme for producing a molecule called NADPH. And NADPH is the primary defense protecting red blood cells from damaging oxidative stress. Think of it like the cell's rust-proofing. Without sufficient NADPH, RBCs become highly vulnerable to oxidative damage from various triggers. These can be certain infections, specific drugs, famously antimalarials, sulfa drugs, some antibiotics, or even certain foods, the classic example being fava beans.
The fava bean connection, I know.
Exactly. So this oxidative stress leads to hemoglobin denaturation. The hemoglobin clumps up inside the cell, forming what we call Heinz bodies. These Heinz bodies then damage the RBC membrane, leading to hemolysis, which can be both intravascular and extravascular. And it's important to remember the inheritance pattern. It's X-linked recessive, so it's much more common and generally more severe in males.
And clinically, how does G6PD deficiency usually present itself? Is it chronic or acute?
That's the interesting part. Most individuals with G6PD deficiency are actually completely asymptomatic most of the time. They live normal lives, until they encounter one of those oxidative stressors we talked about. That's when they can experience an acute hemolytic crisis. Can be quite sudden onset of jaundice, dark urine from hemoglobin spilling out, fatigue, back pain sometimes. The good news is that the symptoms usually resolve once the offending trigger, the stressor, is identified and removed, so things can return to normal.
Okay, so for the MLS, seeing a patient potentially in this acute crisis, what are the critical lab findings you'll be looking for? What confirms the suspicion?
All right, during an acute episode on the peripheral blood smear, you want to look for bite cells. These are really characteristic. They look like a bite has been taken out of the red cell. That's actually where splenic macrophages have tried to pluck out those Heinz bodies.
Ah, okay, macrophage bites.
Exactly. You might also see the Heinz bodies themselves, but here's the catch. They don't stain with the standard right stain. You need a special supervital stain like crystal violet or brilliant crescent blue to actually visualize them, so you have to specifically look. You'll also likely see polychromasia due to the increased reticulocytes responding to the hemolysis.
And the definitive test?
The definitive test is the G6PD assay, which directly measures the enzyme activity. It should show decreased G6PD enzyme activity, but, and this is a huge but, a real diagnostic pitfall, during or immediately after an acute hemolytic crisis, the enzyme activity might paradoxically appear normal.
Normal? Why?
Because the older, most G6PD deficient cells are the first ones to be destroyed during the crisis, what's left behind is a younger population of red cells, including lots of reticulocytes, which naturally have higher G6PD activity. So the average activity in the sample might look normal, even though the person is deficient.
So you could miss it if you test at the wrong time.
Precisely. If your clinical suspicion is high based on the presentation and maybe bite cells on the smear, but the initial G6PD assay is normal, a repeat test weeks later after the crisis has resolved and the red cell population stabilized is absolutely paramount. That's a true diagnostic trap to be aware of.
Wow, okay, that's a crucial takeaway, thanks. Now, our second key enzyme deficiency to discuss is pyruvate kinase deficiency, PK deficiency. Here, the defect is in the pyruvate kinase enzyme, which you mentioned is part of the glycolytic pathway, the main energy generator for RBCs.
Right. PK is absolutely essential for the later steps of glycolysis, specifically for generating ATP. ATP is the energy currency the red blood cell needs to maintain its shape, its membrane integrity, pump ions in and out, basically to stay alive and functional. Without sufficient ATP due to the PK deficiency, red blood cells become rigid, dehydrated, and highly prone to getting sequestered and destroyed by the spleen. Unlike G6PD deficiency, which often causes acute episodes, PK deficiency typically results in a chronic hemolytic anemia starting from infancy or early childhood. It's inherited in an autosomal recessive pattern, meaning you need 2 copies of the defective gene. Clinically, patients present with that chronic hemolytic anemia, jaundice, splenomegaly, and often gallstones later in life due to the constant bilirubin overload.
Okay, chronic hemolysis this time. What's the lab picture for PK deficiency? Are there specific features that help distinguish it, especially from, say, HS?
Well, you'll definitely see signs of chronic hemolysis. A markedly elevated reticulocyte count is usually a key indicator, often very high. The definitive diagnostic test, of course, is the pyruvate kinase assay, which directly measures the enzyme activity in the red cells. It will show decreased PK enzyme activity. Now, interestingly, when you look at the peripherent blood smear, the red blood cell shape is generally normal, or you might see only slight poikilocytosis, maybe some acanthocytes, but crucially, you will not typically see spherocytes. That lack of spherocytes is a major point helping to differentiate PK deficiency from hereditary spherocytosis, which also presents with chronic hemolysis and splenomegaly.
That's a really helpful distinction. Smear morphology is key again.
Always. And treatment-wise, blood transfusions may be needed for severe anemia. Splenectomy can sometimes reduce the transfusion requirements by removing the site of destruction, but similar to what we mentioned for OHS, splenectomy and PK deficiency also carries an increased risk of thrombosis later on, so it's a careful decision.
Okay. We've covered a lot of ground. Membrane defects, enzyme issues. So stepping back a bit, what does this all mean for you? The MLS at the lab bench. How do these intricate pathophysiologies translate into those actionable laboratory findings that guide the diagnosis and really make a difference?
Yeah, this is where you really connect all the dots we've been discussing. The general laboratory findings that indicate any kind of hemolytic process are your immediate first alert. You'll spot evidence of that increased red blood cell destruction, consistently elevated indirect or unconjugated bilirubin, elevated LDH, and critically decreased haptoglobin. Haptoglobin levels drop because it binds avidly to all the free hemoglobin being released from the destroyed red cells. So low haptoglobin is a sensitive marker of hemolysis.
Right. It gets used up.
Exactly. And in cases where there's significant intravascular hemolysis, you might even see free hemoglobin in the plasma or urine, hemoglobinuria, or hemosiderin in the urine sediment later on. Then, alongside the destruction, you'll also see evidence of the bone marrow compensating that increased red blood cell production. That means a robustly elevated reticulocyte count and visible polychromasia, those larger, bluer cells on your peripheral blood smear. These are the immediate signals telling you, okay, hemolysis is happening, now I need to figure out why.
Perfect. So to bring it all home, let's quickly reemphasize those specific lab tests that are indispensable for identifying and differentiating these hereditary hemolytic anemias we've explored. Let's connect them back. Your complete blood count, CBC, is absolutely fundamental. You're paying close attention to the MCV, the MCHC, and the RDW, looking for the specific patterns we talked about in HS, high MCHC, HPP, very low MCV, and stomatosis, high or low MCV.
Absolutely. The CBC provides the initial framework.
Then the peripheral blood smear. We keep coming back to it, but it's truly paramount for morphology. It's where you visually confirm the presence of spherocytes, elliptocytes, stomatites, bite cells, Heinz bodies with the right stain, or those fragmented cells in HPP. This is often the single most telling piece of evidence.
Couldn't agree more. Morphology is king here.
Your reticulocyte count is always critical as that initial indicator of the bone marrow's response. The osmotic fragility test, while maybe less common now with flow cytometry methods emerging, remains conceptually the gold standard for hereditary spherocytosis, and its variable results are also informative in stomatosis.
True, it demonstrates the functional consequence of the membrane defect in HS.
Of course, the G6PD assay and the pyruvate kinase PK assay are your definitive enzyme tests for those specific deficiencies, remembering the timing caveat for G6PD.
essential for pinpointing those enzyme issues.
And finally, never ever forget the direct antiglobulin test, DAT. It's absolutely essential for differentiating these hereditary, intrinsic problems from acquired, often autoimmune causes of hemolysis. The DAT will be negative in these uncomplicated hereditary forms.
A crucial differential test rules out the immune component.
Wow, we've really navigated an incredible journey today, haven't we? Through the complexities of hereditary hemolytic anemias, from those intricate membrane defects that literally reshape red blood cells, to the crucial enzyme deficiencies that compromise their very function and survival. We've truly seen, I hope, the power of understanding both the underlying why, the pathophysiology, and the specific what, the laboratory findings that guide your diagnosis every single day.
And this, I think, raises a really important question for you, the medical laboratory scientist listening right now. Despite the clarity we've gained today on these specific, maybe more common hereditary hemolytic anemias, what ongoing challenges do you face in accurately diagnosing and classifying the more rare or perhaps atypical presentations of these conditions? Think about those cases that don't quite fit the textbook picture, maybe with subtle findings or mixed features. How might continuous learning, maybe closer collaboration with hematopathologists or clinicians, and just that critical thinking aspect be even more essential in unraveling these particularly complex cases in your daily work? Something to reflect on.
That's a great thought to leave everyone with. We sincerely hope this deep dive equips you with, well, a sharper lens, maybe a bit more confidence, and certainly an even greater appreciation for the subtle yet profound mechanisms at play in hereditary hemolytic anemias. Keep asking those questions. Keep digging for those insights.